An IoT reference architecture is a strategic blueprint outlining the key components and their interactions within an IoT ecosystem. It provides a solid framework for designing, developing, and deploying effective IoT solutions, ensuring a cohesive and scalable system architecture. The reference architecture details the foundational layers and components necessary for the smooth operation of IoT systems. Each layer facilitates efficient data collection, transmission, processing, and utilization within an IoT ecosystem. The basic and standard IoT reference architecture comprises 4 layers: perception, transport, processing, and application. The perception layer is the foundation of the IoT ecosystem. It interacts directly with the physical world. It includes various IoT-enabled devices, sensors and actuators that collect data or affect the environment. Typical components of the perception layer include sensors that measure physical parameters such as temperature, humidity, pressure, light, motion, and tension. Actuators that put an action to the world, such as motors and relays. And IoT devices themselves: smart gadgets, cameras, wearables, smart home appliances, industrial IoT machines, and so on. This layer's general functions include collecting the raw data from the environment and executing actions to the world in response to the external, user or machine-generated commands. Recently, this layer's functions have been extended with helpful data processing capabilities like securing sensitive data and providing distributed edge computing capabilities, which are great for simple AI-based tasks. The transport layer, also known as the network layer, facilitates connectivity between IoT devices and the broader system. It ensures that data captured at the perception layer is reliably transmitted to data processing units. This layer provides various communication models, including device-to-device and device-to-cloud communication. The layer is comprised of networking infrastructure, such as interfaces, gateways, routers, modems and switches, and traffic management utilities. Protocols for high and low-level communication. Connectivity technologies for short, medium, and long-range communication scenarios. Common tasks implemented by this layer include bootstrapping the networks and their maintenance, particularly handling IoT devices discovery, authentication, and network management, ensuring seamless and secure data transmission among all IoT actors, and bringing the gap between the local IoT systems and centralized data platforms, just such as clouds. The data processing layer is responsible for all data processing tasks. It can occur in several locations of the IoT ecosystem, including the edge, fog, and cloud. Edge computing devices are processing units that enable near real-time data analysis, reducing latency and bandwidth usage. They are close to the perception layer and usually share a single device or MCU with it. Fog computing devices are components located between the edge and the cloud. They provide distributed computing services that allow advanced data operations on a limited scale and enable advanced IoT data security scenarios and artificial intelligence-based local data processing. They also optimize data transmission through aggregation and preprocessing for cloud platforms. Cloud platforms are centralized systems for large-scale data storage, advanced analytics, and extensive AI tasks such as machine learning and models training. Data pipelines are tools for data ingestion, transformation, and integration with enterprise systems. Artificial intelligence and analytics engines involve algorithms and tools for predictive analytics, anomaly detection, and decision-making. The data processing layer typically performs data processing activities such as cleansing and normalizing raw data, performing analytics to extract patterns, trends, and actionable insights, supporting automated decision-making and triggering responses in real time. The application layer is also known as the user interaction and value creation layer. The application layer transforms processed data into end-user functionalities and value-driven solutions. It allows users to interact with and benefit from the IoT system, while a user is considered not only as a human, but also by other ICT systems, particularly AI agents. The application layer is composed of applications that are solutions tailored to specific use cases such as smart home automation, industrial IoT monitoring, and healthcare diagnostics. Visualization tools such as dashboards and reporting systems that intuitively present data insights. APIs and integration services that enable connectivity with third-party applications and systems, while API stands for Application Programming Interface. Typical functions include providing user interfaces for monitoring, control, and configuration, supporting real-time decision-making and alerts, and driving advanced and application-specific use cases, such as automated workflows, AI-driven decision support, and predictive maintenance.